Hi everybody, I hope that you are having a good afternoon. We are back here for Chemistry 140, which means that, interestingly enough, having it be week 4 of the quarter, we're actually going to do chemistry tonight, believe it or not. No math, no convert miles to barleycorns, or turn how fast a horse runs in furlongs per fortnight to squips per joule or anything stupid like that. We're gonna actually do chemistry. Yeah, we're gonna talk about matter and stuff. But before we do that, I do want to remind you that there is a quiz due tonight. So that quiz is on Unit 3, and it is a soft deadline tonight. I'm just stretching, don't mind me. Soft deadline, make sure you get it in by tonight, but if you need an extra day, totally okay. Absolutely need it in by tomorrow, though. There will be another quiz going up probably tonight, maybe tomorrow. It's hard to say how fast we'll do Chapter 6, but Chapter 6 is the last in the 4, 5, 6 quiz set, so you'll get a third quiz on those 3 chapters. Chapter 6 isn't that long, but there is some stuff in there that is going to be tested on, and there's also some stuff that's important for later. And then finally, we're going to talk about lab number 2 this week at some point. I might do it tonight. We'll see. Totally depends on how far I get through these slides. So, Chapter 6 starts with this sort of heads-up slide. And so, this is the polyatomic ion slide. So, in Unit 9, we're going to be using the polyatomic ions. And Unit 9 is going to come up pretty quick, considering that Week 6 is when we start 9 through 16. I'm going to test you on 1 through 8 on the exam at the end of Week 5. But starting with Unit 9, we're going to refer to these things called polyatomic ions. Polyatomic ions are groups of ions that stick together, or they're groups of atoms that stick together, and they form a charge. We're going to talk about what they are, how they form, why they're relevant, what they're used for, stuff like that. But what you're going to need to do before we get to that point is, because I'm going to just start calling things carbonate and poly isn't one of them, phosphate and sulfite and nitrite, and I'm going to just refer to these by their names. I'm going to expect that you know what they are. So you're going to either need to constantly be looking these up in a reference sheet, which is super frustrating, or you want to commit them to memory because you're going to be using them a lot. If you are a biologist or a material science major, you are going to see these all the time. Biology especially, because in biology you need to know what carbonate and phosphate do, because things like a phosphate buffer, what is that? That's important for physiological pH. If you're a material science engineer, you need to know that for specific minerals, for example. If you're a geologist, this is also really relevant to you. So it's worth committing these to memory because it will save you a lot of time later. We're not going to use them for 2 weeks, so I'm not going to mention them other than that, but there are a lot of them, okay? And they're on the next slide, so depending on what text you're using, you're going to have a list of these available, but I want you to use the list that's here because this is from the 161 text. And if you memorize them now, then when in 161, when your instructor, presumably me, although I'm not teaching 161 in the fall, I'm teaching 140. I teach a lot of 161, and when we get to 161, we start naming stuff. It's like, I hope you know these. I really hope you know these, because here we go. All of that said, I'll put them on the screen here. This is not all of them. There is a second page, so you'll want to know the name of the substance as well as the formula and its charge. Okay, the whole thing is important. Only one of these is a positive charge, and that's ammonium over here. All the rest are anions. So those are all minus signs that come after the last character in the formula. What was I going to say? Oh, this is an online class, so obviously you don't have to memorize anything, right? So have this chart handy. Have page 2 handy. Here it is. But remember that every time you're looking up stuff on a chart, that eats up time, right? So the most efficient way to prepare for the exam is to commit these to memory by doing exercises that involve them and then becoming proficient in them. So you know, oh, I know what bromate is. Oh, I know what fluoride is. Oh, I know what... Well, fluoride's not one of them. I know what nitrite is. I know what azide is. I actually don't know if azide's in your list. It's not. That's fine. There are more polyatomic ions besides these, so I'm just starting to list off other things that exist. Like citrate is one that exists. Like oxalate exists, but those are more important for biology. These are more inorganic, but I want you to know all of them if possible. There are some tricks to memorizing them. There is a relationship between 8 and 8. And that is, if you know everything that has 8 in it, you just commit it to memory. So sulfate is SO4 2-. Just remember that. Nitrate is NO3-. Just remember that. Then anything that has ite has 1 fewer oxygen than the 8 form. So if you know nitrate, so If you know this one, then you automatically know this one too. And my minus kind of got lost under that 3 there. Boop. There we go. And then hypoite has 2 fewer oxygen than 8, and then per 8 has 1 more oxygen. So you can get a whole bunch of them by memorizing everything that ends in 8. Some of them, though, you'll just have to commit to memory. Like cyanide, there's no pattern. You just remember CN minus. Just got to know it. Okay. So whatever strategies you want to apply, you can flashcards, you can go find the Quizlet that everybody likes to do. There's like this Quizlet app where you like shoot asteroids with your spaceship by typing in the name of the polyatomic ion. Like people like to do that. Just make sure there are no typos or errors in it because I know that they exist. I remember trying one that a student recommended, and I got to like permanganate or something, and it wouldn't expect my spelling, and it was because they misspelled it. So just be mindful of that. All right, let's talk about Unit 6, which is matter. Why does matter matter? Why do you matter? Because you're made of matter. That's why you matter. If you're confused, don't worry. You won't be after we talk about matter. Matter is pretty straightforward. It's all around us. You've interacted it. You're made of it. But we do it to define it. On the screen, we have 3 different things. So I have the statue of this orc. He's sitting in my living room. He's like a foot tall. Maybe not even that tall, actually. Maybe more like 8 or 9 inches tall. So it's not really an actual statue. It's just a little figurine. And then I have this cup of coffee. I don't actually drink coffee. So that one doesn't apply to me. And then I have a balloon. Everybody has balloons lying around, right? If you inflate a balloon, there's a gas inside. If you pour a cup of coffee, there's a liquid inside. And orcs are solid. I mean, just look at those packs, right? So those are the 3 states of matter that we're going to concern ourselves with. Solid, liquid, and gas. We're going to define these more rigorously in just a second. But all of them have something in common. And that something in common is that they occupy space. I cannot put something else in the same space as occupied by the coffee cup, nor the coffee. If I like drop a block of copper into the coffee, not only will it taste terrible, but the coffee will get displaced. It will go upward and not share the same space as the copper block. When I inflate the balloon, the boundary of the balloon expands because the gas is occupying that space. And for solids, if you try and put 2 solids together, like if you try and put your hand on the table and pass it through the table, you can't do that. The table occupies its space, and I occupy mine, and they can't share. The other thing is that they have mass. Everything that is considered to be matter has mass associated with it. That means that if you are in a gravitational field, such as the Earth's gravitational pull, you will exert a force in the direction of the core of the Earth. You could go to the moon, you would still exert a force because you have mass. Mass is attracted to other mass. If you have those 2 properties, you take up space and you have mass, you matter. If you don't have those properties, you do not matter, you energy. Energy is different than matter, but they're related. What about plasma? Plasma is a gas that is ionized. So things like fire or the sun or lightning, those are examples of plasma, but they're not common enough that we can work with them in the laboratory in a safe and controllable way. So we leave that to the physicists and or higher level chemistry courses. There are interesting things that you can do with plasma for sure, and you can safely make it in the microwave, but we're not going to cover it in a lot of detail. In fact, I think I mentioned that. Yeah, here it is. A plasma is a stream of ionized gas. We're not going to cover it any more than that. We are going to talk about these 3 phases in a bit of detail, and there are more than 4 phases. In fact, there are multiple ways to define solid for many substances. For example, sulfur has two solid states. It has the rhombic state and then the monoclinic state. I was like, is it just regular? Carbon has multiple solid states too. There's diamond and then there's graphite. They're different, but they are both solid. So saying solid is a little bit of a it's a little bit too generic. Fork wrapped in tinfoil microwave experiment. I have never done that because I've never had a microwave that somebody has been like, here, just do random stuff to it. So like, I have a microwave, but I don't want to ruin it. And I know I'm not going to, but like, still. Like, I know all about put the aluminum CD in the microwave and hit go, and then you get fireworks. But, yeah. Now, why do we care about how phases interact and behave and whatever? Well, that's actually all we care about. Chemistry is defined as how matter interacts with other matter. Now, whether it does transform or not is of great interest to us. For example, if I sit on my chair wearing, like, I don't know, like fabric clothes, denim. That's the word I was thinking. I'm wearing jeans. If I sit on a chair wearing jeans, and the jeans react with the chair, that would be bad. Obviously, we don't want that. So we should design our chair or our jeans so that they don't react. So making pants out of, say, sodium metal would not be a good idea. Making them out of polyester and then sitting on a chair made of acid would also be a bad idea because they react. Just don't sit on acid in general. Non-Euclidean liquids and solids, so like ionic solids or ionic liquids, stuff like that. Bose-Einstein condensate, supercritical fluid. We're not going to deal with those terribly much in this class, although we will mention them when we get to phase diagrams in 162. I think supercritical fluids are cool. Are they practical? I mean, if you want to dissolve chicken fat, apparently, yes, but there's a lot of weird stuff out there. We're going to keep it basic for Chem 140 because that's what we need to know. This screen shows you the way in which we can define a solid, a liquid, and a gas by using an actual trait that we can observe or measure. So the first trait we're going to look at is shape. Shape is the rigid three-dimensional space that something occupies. For example, a solid shaped like a cube, no matter what force you apply to it, it will remain a cube. Unless you apply great force to it. But I'm just talking about, like, you drop it, or you bop it, or you twist it, or turn it, or whatever. Solids remain the shape that they are. Liquids have a very fluid shape, though, which is why we call them fluids. Liquids occupy the shape of their container. So here, if I draw this, this is the shape of my liquid. It's right here. Because the container is shaped like that. Now, if I had a different shaped container, a differently shaped container, let's say this is 20 milliliters or something, and this is the 20 mil line, then the shape of my liquid would be this. Now, in each of these cases, the amount of liquid is the same. So shape and volume have different ways of interacting with our senses depending on what phase we're looking at. So in this case, the volume remained the same, even though the shape is different. In the solids case, if the shape is stuck how it is, the volume can't change no matter what. Now, you can use mass, but you can't use mass to define a state, because changing the state does not change the mass. So, for instance, if I had 20 milliliters of liquid, and I went and weighed it, and then I threw it in the freezer, and then while it was still frozen, I weighed it, then the mass would still be the same. So, we can't use that as a rubric, unfortunately. Now, density might be able to be used. For example, solid water has a density less than that of liquid water, which is why water and ice, when mixed, the ice floats to the top. So that might be what you're referring to, but the mass strictly by itself, we can't use that to differentiate phase. When you have a gas, the volume of a gas is always the volume of the complete container that it is in. Now, if you open this, then the volume of the container is the atmosphere, and so the gas will just go voomp everywhere. If you blow a balloon up with helium, then the volume of the helium is the volume of the balloon. If you put more helium in there, it will expand and the volume changes. So its shape and volume are both variable depending on circumstances. Now, the shape will also change if you squish the balloon. If you pop the balloon, then the volume again becomes the volume of the atmosphere. Water expands due to its density change, yeah. So as you heat water up, its density gets lower and lower and lower. So if you like put ice in boiling water and it stays ice, it might actually sink to the bottom because its density would be higher. The density curve for water, by the way, looks kind of like this. Water is one of the only liquids that does this. So at 4 degrees Celsius, its density is 1 gram per milliliter, and it does something like this. My maximum was supposed to be at 4, but I sort of drew the line really flat. So water is very bizarre, but because it's bizarre, all life on the planet exists. So that's kind of useful. I just want to get the picture up here before I talk about this mass stuff. So mass is an important property to understand conceptually, but there's a lot of ways you can mix it up because the term weight is also thrown around. These are different terms. And the best way that I can describe this is by writing this equation. If you've ever taken any sort of physics class, you know about Newton's law of acceleration. F equals ma, right? What this is saying is that if you are a mass inside some sort of acceleration, such as, say, gravity, then you will accelerate in the direction of the gravitational attraction, and you will have a force exerted upon you or whatever surface you're standing against or whatever. So this right here, m, is your mass, but this right here, f, is your weight. So if you are standing on a scale, so here is me on a scale, the force that I am pushing down is my weight. But how much stuff I am made of is my mass. In other words, the amount of mass that you have is just constant no matter where you go. But your weight depends on where you are relative to another celestial body that has its own gravitational field. For example, the gravitational field on Earth is this, 9.8 meters per second squared. But on Earth, it's this. So G moon is 1.62 meters per second squared. How do I know that? Because I just looked at the thing and divided by 100. I was going to get my calculator out, and I was like, oh, no, I'll just divide by 100. Everybody knows this number, right, though? You've probably heard that that's how fast the gravitational acceleration is on Earth. On the moon, it's about a sixth of what it is there. Now, you still have the same mass because you're made of the same amount of stuff, but your weight is reduced. Best weight loss plan ever. Go to the moon. The weight just melts right off. Now, I didn't know if your sentence there said for us Freedom Unit people or if you meant for U.S. Freedom people. But yeah, so pounds, when you measure your weight in pounds, what you are actually measuring is a force. The actual unit of mass in the imperial system is called the slug, which is another reason why imperial units are dumb. But yeah, the pound is actually this right here. And so your weight in pounds will change on the moon, but your weight in slugs or your mass in slugs would not. And because that's all obnoxious and confusing, and we also don't want to ever deal with gravity, right? Like, we don't want to deal with this. Not that gravity is something that changes very often on Earth. Like, it will change based on elevation. Like, the further you are from the Earth's core, the less gravity you experience, right? But it's very, very slight at this elevation. Like, you'd have to go hundreds of kilometers up for it to be a noticeable difference. But if you're doing very, very minute physics experimental work, then that matters. For our purposes in chemistry, it doesn't. So we don't want to just multiply everything by 9.8 every time. So we just don't. We just deal with mass. But it is important to know the distinction. So just be aware that there is one. Wow, I missed my arrow there. There we go. Now, when you do any reaction, the transformation involved is going to either be chemical in nature or physical in nature. Is there such thing as zero gravity? Yeah, if you were far enough away from any celestial body, well, I don't know if, like, so that's a hard question for me to answer because I can't envision a point where you are so far away from anything that you have no attraction to anything. Now, you wouldn't feel that because you would probably be accelerating towards it. You would just feel weightless. Now, there are specific areas around Earth and the moon, like very, very specific points where the gravitational pull by both entities is the same. And thus you feel pulled equally in both directions and you just don't move. So that's called the Lagrange point. And I think it's spelled like this. And so if you want to do some fun reading on Wikipedia about, like, hey, can I go somewhere where there's zero gravity? Yeah, find the Lagrange point. Technically, you would just stay there because both things would pull on you away from each other in opposite directions. Now, you could move orthogonal to that, and you would exit the Lagrange point. But it is a thing that exists. Now, when we do any reaction or process, I said reaction earlier, but I meant to say process. You may transform your matter, or maybe you don't, but how much of it that you have is always going to remain the same because all you're doing in a reaction is cycling electrons around or exchanging which atoms are paired with which other atoms. All of the matter that's there, though, remains. You can think of it as a jigsaw puzzle. Maybe your jigsaw puzzle is unusual in that you can put it together two different ways. And if you do that, you still have the same number of pieces before and after you do the puzzle, regardless of what outcome you have. Now, if each of those pieces was, say, an atom, and all of the atoms are accounted for, the amount of matter that you have in your reaction or process is going to be constant. And this is called the law of conservation of mass. And it's very easy to see this in principle. Just take any bottle that you're going to put a reaction in and seal it shut. Beer is a great example of a chemical reaction that follows the law of the conservation of mass. If you put the substances into your bottle and then seal it shut with a bottle cap, and then the fermentation process happens where the yeast or the stuff that you put in there ferments with the sugar to make ethanol and CO2. All of that stuff undergoes a chemical reaction. You don't start with ethanol. You don't spike your own beer with ethanol in the beer making process. Although I'm sure that there is beer out there that is spiked with ethanol because that's like a shtick that they have or whatever. But if you weighed this bottle beforehand, I have the wrong pen selected. Oh goodness, I selected the wrong thing. There we go. If you weighed this on a balance, you might find that, oh, it weighs, I don't know, this much. That's a lot of beer now that I think about it. That's like over a pound of beer, but maybe that's not. I don't know. I'm just guessing a number. And if you weighed this afterward, you would get the same result. I'm gonna have to go weigh like a bottle of beer now after this lecture, just because I'm just trying to estimate. You get the same result. That's the conservation of mass. Now, if you open this bottle, then the CO2 will escape, and then the mass that you have will go down slowly over time. That does not mean that the law of conservation of mass was violated, though. It's just that you cannot weigh things that are not in the container. So that is something that you can do as an experiment. I know a lot of physicists actually do stuff in their physics classes, and they approach me with questions like, how do I figure out how much the mass of a spray of compressed air is? And the answer is, oh, you weigh it before you spray it, and then weigh it after, and the difference must be what you ejected. I know I had people in physics come to me to ask, like, hey, can we do a calculation to figure out how much stuff is in there? And I was like, well, yeah, but you could also just weigh it. And so they did that, and they were like, wow, that's so much easier. Yeah. So the conservation of mass, super practical. Just keep this one in your pocket, because mass before has to equal mass after, even if that mass is somewhere else. Here's a practical example of that. So let's suppose that I have 50 grams of water and 10 grams of Alka-Seltzer, and I mix them. And I let it bubble and fizz, and I don't remember what the slogan was for Alka-Seltzer. It was something like bubble and fizz, gee whiz, or I don't know. And then when we're done, this is the mass that we have. So what's the mass of the CO2 in the reaction? How would you find that? Would there be a way to count for, say, propellant in a situation like that? Well, for compressed air, it's 100% propellant. So yes, actually. In some cases, maybe you could look up the ingredients and see like what percentage of what's in there is propellant, and assume that you have a homogeneous mixture when you hit the button. That's the best that I could do. If you wanted to do like a chemical analysis of it, you'd have to spray that into like a container and then like GCMS or EA. Sorry, I should not be using acronyms that you guys don't know. You could gas chromatograph, mass spectroscopy, your sample just to see like what proportion of what it is. Or elemental analysis would tell you what the percent composition is. Nah, that probably would be super useful. Gas chromatography would probably be the best way to do that. If you just spritz that into the injectors of the gas chromatograph, because it will then send all of your gas through a column. And then it hits a detector and you can see what it is. Going back to this question, well, if I started up here with these materials... Oops, where'd my pen go? I'm using the wrong end of the pen, that's why. If I started with this much stuff here, this is 60 grams, but here I only have 57.9. So the missing, I'm going to put it in scare quotes, missing 2.1 grams must be the CO2 that escaped. When we talk about gas chromatography, we don't really do gas chromatography here at Everett, which I find to be kind of a shame because I did a lot of it in college and it's pretty useful. Like, I am technically an expert in gas chromatography and mass spectroscopy. We don't do GCMS here because we mostly do NMR. And I am also an expert in NMR. NMR is much more useful. We're going to do NMR with you guys in 163 if we can get back in the classroom. But NMR is basically put your sample in the tube. The tube is a giant magnet. It spins like crazy. And then the computer spits out a, like, what basically amounts to a code. Like, I want to say, like, the best analogy I can make for NMR is, like, it's like learning how to read a QR code like what everything on it means. I was going to say barcode, but I think a barcode is a little too simple. You get lines that, depending on the shape of the line and then where on the x-axis it is. Sorry, I hit my mic there with my hand. You learn stuff about it. So there are ways to find these things out. There are all sorts of things that matter can do. And we've spent a lot of time talking about just random things. I'm going to give you some simple examples here on the screen. Like, you can melt stuff, you can burn it, scorch it, dissolve it, measure it. You can measure matter. There are some actions that you do that just don't even affect the matter in any way. So, for example, if I look at something and recognize, oh, this statue of an orc I have on my desk is blue, because it's a Dragon Quest orc. I don't change the statue of it in any way by looking at it, because I don't have Superman X-ray eyes. I don't emit X-rays. At least I hope not. But other things that I could do, like, for example, if I took this piece of paper on my desk and then lit it on fire with a match from the kitchen or something, that would definitely change the matter in an irreversible way, or at least seemingly irreversible way. We're going to use this as our guide. If the identity is what we're going to care about, is the action that we're doing changing its identity more or less permanently? So let's look at some examples of that. First, let's define our terms here. Properties are any characteristic that define something as distinct from any other thing. So, for example, water is a liquid at room temperature. You could use that property of water to distinguish it from any other thing that's not a liquid at room temperature. So, water would not be, say, ceramic. Water would not be plastic, because those are all solids at room temperature and water's not. Now, obviously, there are multiple things that are liquids at room temperature, so you'd have to use different properties. And eventually, you give something enough properties, like in 20 questions, you give it enough properties, you eventually narrow it down to one thing. A change is any action that invokes a change. Like, duh, right? So, if I were to cause ice to melt into liquid, water, that would be a change. Melting is the change. If something gets moldy because it has been left in the pantry for too long and you didn't eat it, you could always use that bread tomorrow. And you say that for 2 weeks, and then, oh, now you can't use the bread anymore. It's moldy. The action that causes it to change is molding. If you let iron rust because you left your motorcycle in the rain at the EVCC parking lot for 14 years of working there. Not really a true story. I've only been working there for 11. I just said a random number, but my poor Harley is very, very rusty, and that is definitely a change. It was not rusty before, and it is now. So, these are all changes that can happen to matter. So, we're going to look at both properties and changes, but we're going to look at them from this perspective to identify the nature of the action occurring. So, whatever our action is, and our action might just be observing a property or invoking a change, we're going to look at the chemical formula of a substance before and after that action. Now, this is an introductory chemistry course, so you might not have seen many chemical formulas. That's pretty much okay for now. You're going to pick up on formulas as you go. You know enough common ones to be able to do basic examples, and then for the more complex stuff where even I couldn't tell you the formula, like, what's the chemical formula of pepperoni pizza? Like, I couldn't tell you that because it's a mixture. You're going to be able to make predictions based on intuition and what your senses tell you. So, we're going to use the formula as the guide, but even if you don't know it, you can still interpret and infer enough about it. The first definition that we're going to discuss is physical change or property. If you do something to matter and its chemical formula remains the same, what you've done is physics. You did not create a new substance. You did not do chemistry. The things that are physical by nature are always phase changes and anything that is just a general observation. However, other things can affect that too. For example, if you take aluminum and you put it under the 1,000-ton press. I was watching this video last night because I was following links on YouTube, which I think were from people in Discord from this class, actually. And I was watching, there's a guy out there who just puts everything under the sun under his 1,000-pound press and just presses it. And most of the time it breaks, of course, because it's 1,000 tons, right? Maybe it's 100 tons. I don't know. It's a lot of tons. But if you change the shape of something, it's still the material that it was before. So an example of that would be like they were pressing an aluminum foil crumpled into a ball. They pressed it into a coin. The coin is still made of aluminum foil. It's just now in the shape of a coin. So it would actually do the same chemistry as an aluminum piece of aluminum foil would. It's just more dense because it's been compacted down into a tinier space. So these are all examples of physics. We're not doing chemistry here because the identity is the same. And if the identity is the same, the formula is the same. When you melt water, the ice it started at is still water. It's just water in the solid state. Liquid water is water in the liquid form, of course. They both have the same formula because they are both water. And so we could conclude that, oh, okay, this is a physical change. Now, you are sort of taking that on faith, I assume. Because how would you know? Well, we know after doing enough experiments that if we examine the properties of water and its crystal structure, you can actually see the molecular shape of it in the crystal structure. You could do that with water in the liquid phase by different means. You don't get a crystal structure out of it, obviously. But you can examine its properties, you can measure its bond angle, etc. You get the same result. It's the same molecule. Here's another example of an obvious physical change, but a little less obvious to work with because we don't really know the formula of paper. I can make a guess at the formula of paper. So paper is a carbohydrate. It's cellulose, the component of cell walls, or glucose as a disaccharide with a beta anomeric linkage. Those are words that exist, and you probably don't recognize them. But I teach biochem, so I know what goes into cell walls. That's like the one thing I know about. You get this polymer, and that's cool and all. So I know that it's the same before and after. But if you didn't know that, then you can work around that by just asking yourself intuitive questions. Okay, is the paper I tore usable in more or less the same way than it was before I tore it? And the answer is yes. You can write on paper. You could fold the paper. It's just a little smaller. Another good rubric is, can I undo? And you might think, well, it's hard to undo a tear, right? But no, you just tape it back together. And then you get a piece of paper that's more or less functionally the same, right? So you can apply tape. Tape doesn't change the nature of the matter in any way. You aren't doing chemistry by applying tape. In the ice example in the previous slide, can you undo? Yeah, you put it back in the freezer. What would be an example of something you could not undo? Well, that'd be this. If you burn paper, can you unburn it? Like, technically speaking, sure, you could unburn it if you took the carbonized matter and then planted it in the ground, grew a tree out of it, cut the tree down so it was lumber, and then sent the lumber to a paper mill to make it paper again. But that's not practical or easy to do. So your undo needs to be easy. Yeah, lignin, that's the substance I was trying to think of. That's the stuff that you put on paper to, like, repair, like, old historical documents and stuff like that, right? I wanted to say like rubber cement or glue, but those are not very like epoxy. It's not the same. If you're doing stuff with fire, what you end up with is something totally different. And you can do that by looking at the chemical formula. But an easier way to do that would just be to say, okay, are the properties of paper and the properties of ashes vastly different? And then can I undo? And if you cannot undo easily, it's because you've done chemistry. Most chemistry goes in one direction. Now, you can go in any direction you want in chemistry, but most chemistry will go on its own in one direction. And in order to get something to go in reverse, you have to apply lots of energy or effort. An example of this is rust. When you mine up iron from the earth, you do not mine up pure iron. You mine up rust. The rust is like that because, well, long, long ago when the Earth was formed, that iron that was there bumped into a molecule of oxygen, and they got together. And I realize these aren't balanced. I guess I could just balance it real quick. But the iron has been rust for billions of years. But we don't want rust. You can't build a building out of rust, right? So what we have to do is we have to go in the other direction. And that's difficult to do. That requires lots and lots of energy. Most of the reactions that we're going to look at are going to go in the direction that's easiest to go. And we're going to talk about what makes a reaction go in one direction versus the other when we get to equilibrium and thermodynamics in 162 and 163. You might also talk about that a lot in engineering. Engineering does a lot of thermo. We're going to call any process where the undo is difficult and the chemical formula changes a chemical process or a chemical change. A lot of this is kind of hazy gray area intuition. And the definition of, hey, the formula changes, not super useful. Use the undo idea, though. Is it easy to undo the change that you did? If the answer is yes, then you did physics. If the answer is no, odds are you did chemistry. And because this is a chemistry class, we care primarily about the chemical reactions. So that's what we're going to do, is we're going to look at those. So on the screen, I have a bunch of chemical and physical observations, changes, processes, etc. What I want you to do is look at what's being stated there, find the object that is being changed, and tell me if that change is physical or chemical. Then once you've done that, tell me the word that helped you determine, oh, this was chemical, or oh, this was physical. Okay? And we'll go over the answers in about 5 minutes or so. Type in your stuff in the chat, and you can like discuss it or talk it out or whatever. And we'll go over it shortly. See you in a bit. One more minute, we'll go over the answers here. All right, let's go over the answers here. So, whenever you boil anything, boiling is a phase change. And anytime a phase change is invoked is a physical process. So, water being boiled to make delicious pasta, you're just turning your water from liquid to gas. It's still water, though, and you could condense the gas to get the water back. Grape soda is observed to be purple in color. Well, when you look at something, you aren't changing it in any way, so that's physical. So, looking at something and reporting its properties is always a physical observation. Alka-Seltzer is dissolved in water, releasing a gas. Now, you might think that this is the one you want to look for, but watch out. Dissolving in water can be both physical or chemical, because all dissolving means is that you don't see it anymore. It's still there. Like, Alka-Seltzer dissolves in water, but so does table salt. You can get the table salt back by boiling the water away, but if you boil Alka-Seltzer in water, you don't get Alka-Seltzer back. You get sodium citrate, which is not. Is it sodium citrate? I'm trying to think. Yeah, it totally is. Okay. And the reason for that is because you've released a gas. This is the important one that tells you what is going on here. Sodium metal is melted. Melting is a phase change. Igniting anything like a candle, a lighter, your barbecue, gunpowder, those are all chemical reactions. You cannot ignite something twice. If you did, that would be great. You could just use the barbecue forever. One tank of propane, just keep igniting it. One clump of charcoal, just keep igniting it. Yeah, you can't do that, unfortunately. Air is compressed in a scuba tank. When you compress something, that's just cramming it into a smaller space. Lots of people do this with luggage. They cram their clothes into it. They compress their clothes. All you're doing is making it occupy a smaller volume, but the stuff is still the same, so that's physical. I had I don't know really how to describe her in relation to me. She was my grandmother's sister. So great aunt? I don't know. Anyway, she was a woodworker, and she made all these little woodland creatures. And she would give them to me for like Christmas or my birthday whenever I saw her. But it was only very, 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 very occasionally. So I had like 4 or 5 of them. And they were really cool. I don't have them anymore, unfortunately, because I don't know what happened to them. But when you take a piece of wood and you chip away at it over time, you just make a smaller and smaller and smaller piece until it's the shape that you want. It's still wood, though, and you could use it for any manner of things that you would use wood for. For instance, throw it in a fire and use it to heat yourself, which would be kind of sad. And then finally, combustion. Again, anything combusted or ignited is chemical reaction. All right. I think it's time for a break because we're at the top of the hour, aren't we? Yeah, we're close enough. So when we come back, we'll talk about extensive and intensive properties. But that'll be 10 minutes. That'll be for future us in 10 minutes. Look how close I got to 10 minutes before. We'll just try again. Let's see here. I gotta find the music here. Let me get... Yeah, there we go. So I'll just hit the button. There you go. See you in a bit. Hello. Alright, we're back. Where are we? Oh yeah, we're doing... Oh, that's the wrong one. There we go. We're talking about extensive and intensive properties. This is another rubric that we can use to categorize matter in various ways. We're going to gauge the impact of a property based on the quantity of material present. Some properties do depend on how much stuff is available. For instance, if I gave you a cup of water, there you go, there's some water, and then I gave you a gallon jug of water compared to that. Yeah, my artistic skills leave something to be desired, but that's okay. Which of these has the larger volume? Well, obviously, this one has the larger volume. And this one has a smaller volume. So we would say something like volume depends on the amount. And we'll say that that is an example of an extensive property. Extensive properties depend on how much stuff is present. So something like volume would be extensive. However, if I asked you which of these has the higher boiling point, well, they both boil at 100, right? It doesn't matter how much water you have, water boils at 100. You could boil a cup, you could boil a gallon, you could boil the ocean. You just need the temperature of the substance to be at 100. Now, how much energy you need to boil it, that would be extensive because energy is different than just the temperature that we're measuring. So, if you have a property or trait that does not depend on the quantity that you have, that's called intensive. Now, you're probably familiar with a lot of things out there. So, more or less, this is just going to rely on your intuition. You're going to look at these and say, oh, okay, if I poured more of it, would that change this property? So, for example, if I poured more water, would the weight of my water change? Well, yeah, because weight is a function of matter, and how much matter is present is exactly what an extensive property is, right? Oops, I thought there was something after that. So weight would be an extensive property. So going down this list here, we've already done volume, so volume would be extensive. But try these other four. Flammability, boiling point, mass, and state. Let me know what your answers are, extensive or intensive, in the chat. We'll go over the answers in like 3 minutes or so. This shouldn't take that long. All right, one more minute. I'm getting distracted by my email here. All right, let's go over the answers. I keep answering emails from other people, and more emails appear. All right, flammability is something more flammable if you have more of it. I mean, you will have a larger surface area, but that's not what the question is asking here. It's asking, is it more or less flammable? And, well, it's the same amount of flammable, right? Something is either flammable or it's not. Boiling point, we just did that one. Now, mass, that should be obvious. Matter is the definition by which we use intensive or extensive, so this has got to be extensive. But what about state? State's kind of weird, right? Well, think about it this way. If you pour more water into your container, does the state change? Will you suddenly get a solid, or will you suddenly get a gas, or will you suddenly get a liquid? And the answer to that is in like 90% of circumstances that I can think of, the answer is no. Like, you don't pour more water into a cup, but if you pour too many cups, it becomes a solid or it becomes a gas. Not really. So the best answer for state would be intensive. I can think of one edge case for that. That would be like if you had gas in a balloon and you just pumped more and more and more of that gas in there, it could eventually condense, but that won't always work, and that will depend on temperature. So that would be state and temperature together, probably. All right, let's talk about mixtures. We're going to interact with all sorts of mixtures in this class and in other classes beyond Chem 140. So we need to be able to categorize them so that we know what we're talking about. Now, on the screen, I have two things here. I've got water in a glass, and then I've got cake. Which of these substances would you be able to describe as pure? Unfortunately, the answer is not cake, but if you know where to find pure cake, let me know. Cake can't be pure because it's got a bunch of stuff in it, right? It's got cream, it's got chocolate, it's got cherries, it's got frosting. It's a mixture. So we can either have something that's pure or something that's a mixture. That's the worst R. Boop. And there goes half of my word, of course. There you go. So a pure substance has only one thing in it. A mixture has multiple things. Now, when I say the word thing, I don't mean one element. I mean one thing. So that thing could be water. That thing could be oxygen. That thing could be acetone. That thing could be graphite. Like, I could list any number of things, but they have to be things that I can assign a formula to. Because if I can't assign a formula to them, then they're mixtures, because they're a bunch of things, each with their own formula. So we're going to make a little flowchart here. Is there only one thing, one substance in the material? If the answer is yes, it's a pure substance. If the answer is no, there are multiple things, you have a mixture. So whenever you are given a question, this is the first question you should ask. Is there one thing in there, or is there a bunch of stuff? Then what we're going to do is we're going to separate each of these two things into their own two categories. So we're going to start with pure substances. So when you have a pure substance, there is only one thing in the sample. If we look within the chemical formula of that thing, we can categorize it into one of these two categories. If the chemical formula contains only one element, one type of atom, we're going to call it that element. So diamonds, for example, are only carbon, 100% carbon. Same as charcoal, same as pencil lead. Just in case you didn't know that, diamonds are completely carbon. All diamonds are pure carbon. Now, you may have some impurities in there, which would actually give them colors, which some people find appealing. So there is some interesting aspects of, like, having impurities in gemstones. In fact, all rubies and sapphires are aluminum oxide with impurities in them, which give them the color. If you just had an aluminum oxide crystal, it'd look kind of the same color as diamond. It has no color. But the fun thing about diamond, actually not fun, I should say, it's completely carbon, which means flammable. Do not store your diamonds, like, next to a fireplace or something. They will go up in smoke. This is why jewelry boxes oftentimes have, like, flame-proof stuff or insulation or whatever. Because if it gets too hot, these things vaporize and you no longer have diamonds. And that's no fun. Yeah, you can recreate them, but that's expensive, right? Just don't lose your diamonds in the first place. Now, what if you have more than one element? What if you have two or more? You could have any number greater than one. We're going to call that a compound. Yeah, I'm totally for synthetic diamonds, because, like, if you can't tell the difference, then whatever, right? It's way better that somebody was paid to make it in a lab than some poor kid was forced to mine it up and give it to De Beers. Like, screw those guys. Just give me a lab diamond. Not that I really like diamonds anyway. Like, I'm not really like a gems on jewelry kind of guy. I like steel bands and, like, studded leather. Those are the accessories that I wear. I want my boots to have spikes on them. Like, whatever, right? Anyway, a compound has more than one type of atom. So table salt, for instance, the formula is sodium chloride. So if I wrote it like this, here's an element and here's an element. Where do you find these elements? Well, we haven't really had much opportunity to use p-table in this class, but I'll get the link for you. Oops, I gotta restore the link here. Hold on. There we go. There's p-table. And if you click on that, you'll get a screen that looks kind of like... that's the chat. There we go. Like, what the heck window is that? It looks kind of like this. There you go. And so any substance that contains only one of the things on this table, on the periodic table, would be an element. Anything that has more than one, so here's sodium, boop, there it is over here. And then here's chlorine. We're going to call that a compound. And 2 is not the limit. Like I said before, you can have as many elements as you want in your compound. Things like proteins have tons of different atoms in them and different elements, and I'm trying to think of other things that would have, like, really, really, really complex formulas. Some crystals or minerals have really weird formulas. Tooth enamel has a really weird formula. It's a compound, though. stuff like that. So those are the two categories for pure substances. You can be an element, you have one thing off the periodic table, or you can be a compound, you have multiple things off the periodic table. Let's go to mixtures. Mixtures can be split into two categories as well, and the way that we're going to split this, and this is actually really important for the quiz. I know a lot of my students at 161 had some trouble with some of these questions, but the rubric that we're going to use is, are all the portions identical? If the answer is yes, what you're looking at is a homogeneous mixture. So for instance, in the ketchup here, it would not matter if I use the top of the sample or the bottom of the sample, or maybe even the stuff scraped along the side here. It's all the same. It's all ketchup, right? It should taste the same. It should have the same texture, the same consistency, etc. So this would be an example of a homogeneous mixture. Down here, though, in the salad dressing, you can see that if I scoop from the top and I scoop from the bottom, I'm going to get a very different results. The top is mostly oil in this picture, but the bottom is where all the herbs and the spices and the good stuff are, right? Something that happens naturally in nature could be an element or a compound. It depends on what element you're looking at and how it's formed. Most of the time, you actually get compounds. It's pretty rare to find elements by themselves, but there are some exceptions. So gold and platinum, the noble metals like silver, those are commonly found as elements, but so like iron, for instance, you don't mine up iron, you mine up rust. And so, was it this class that we did that example? It must have been, yeah. So you would find iron as a compound, as iron oxide. Now, the problem with these definitions, homogeneous versus heterogeneous, and some of you are going to fall into this situation where you look at an answer and you're like, I'm not sure. It could go either way. There is some leeway here. There is a middle point where the result that you get just ends up being like ambiguous in some way. And there are some questions on the quiz that are like that. What I want you to do for those questions is use your senses. You could do a little bit of research online if you need to, because remember, you get to use the internet. But think of this statement. Are all the portions identical? And if you can't really tell like how that is from the intent of the question, think about under most circumstances, would all portions be identical? Like, for instance, if you were to scoop water out of a swimming pool, there could be stuff in the water, like little like bits of plastic from toys or string from clothes or like a rock or something like that, or dirt or something. But most of the time, if you scooped water from a swimming pool, 99% of the time, you would get just whatever the water was and whatever was dissolved in there. So obviously, there's other stuff in there. It's not just water, because there's like all the dissolved stuff that you throw in the pool to keep it clean. And so I would call that, the intent for that would be homogeneous mixture. Likewise, if I said, I'm going to scoop up water from the bottom of like a lake bed, down at the bottom of the lake bed, there's all the sediment and there's like rocks and plant life and stuff like that. It's very abundant at the bottom, not so much at the top. So scooping from the bottom, heterogeneous mixture would be the intended answer, as opposed to scooping from the top of the surface, which would probably be homogeneous mixture, because you're just getting the water and very unlikely to get much else. So be careful with specific questions about what they're asking you, because you might see something and be like, oh, I don't know what that is, and then type it in the answer and then get the wrong answer, because I'm basing it on this definition right here, okay? So just be mindful of that. And then if there is an issue, you can always argue it afterward, because I know there are some of these questions that I actually have written all of these questions, and I thought one way, and most students think that way too, but sometimes you have an idea and it's not the same, and that's okay, and we can talk about it. there's our flow chart. You're eventually going to like pachinko machine your substance down into one of these categories. Okay? You cannot do something like this. You cannot something that is a pure substance and then a heterogeneous mixture. That doesn't work because they're not connected, right? So start at the top, ask yourself, is there one thing here? If the answer is no, you're going this way. If the answer is yes, you're going this way. And then ask yourself the next question that you run into until you get the substance that you intend. Or you get the category that you want. This is just a picture from the first textbook. I actually scanned this picture because I liked the picture. And now I realized, like, oh, I could just go to Google. So this is one of my first slides from, like, shit, when did I first start teaching? 2009? I'm old, you guys. Categorize these substances for me. So one of the 4 categories at the bottom, each of these should fit into it. Either element, compound, homogeneous mixture, or heterogeneous mixture. Be mindful of what I'm putting in parentheses. When I write something in parentheses, the reason for that is because this is what the sample contains. So for instance, nail polish remover is just this. This is its formula. For this example, right? So not all nail polish remover is 100% acetone, but for this specific question, it is. Okay. If you aren't sure, go ahead and ask. We'll go over the answers in about 5 minutes. How are you doing? One more minute? We'll go over the answers then. All right, let's go over the answers here. So, if you look on the can, I guess Red Bull comes in cans and not bottles. I almost said bottle. I don't drink Red Bull or any energy drink, but usually they come in cans. But on the side of the can is the container, the ingredients. I don't know why I said container. I'm just full of the wrong words today. On the side of the container is the ingredients listing, and the ingredients listing tells you right away pure substance or mixture. If there's more than one ingredient, it must be a mixture. So Red Bull is definitely a mixture. Now the question is homogeneous or heterogeneous? Well, when you open it, if you drink it from that state, it is intended to be a homogeneous mixture. If you pour it into like separate cups and then everybody takes a shot because it's a party, I don't know. Don't mix uppers and downers, guys. That's a bad idea. Um, the intent is that this should be homogeneous. Now, is there a circumstance where it could be heterogeneous? Yeah, like if you backwashed or something, and then like the bottom of the container or the saliva gall goes to the bottom. I don't know, something like that. That's gross, though. All right. How about nail polish remover? Nail polish remover, there's only one substance in this specific nail polish remover. This is acetone brand nail polish remover. And here's the formula. I gave you the formula because not everybody knows what the formula of acetone is. So there's only one thing in here, so it's a pure substance. And because there is more than one element, there's C, H, and O, this would be a compound. What about the next example? Poorly mixed gravel. So here's how I'm going to make gravel. I'm going to put some sand in, some rock, and some salt. I don't know why the salt. But I'll just pour them all in there, and then, I don't know, I'll shake it a little bit or something. I just don't have the energy to really do this project. So I don't mix it very well. So what would happen? Well, most of your scoops are going to have more of one thing than the other two, probably. In fact, whatever you poured in last, probably going to get a lot of that for the first few scoops, and then almost none of it at the bottom, right? So heterogeneous. So you can see the intent of these questions. Like, is it a little bit ambiguous in some cases? It kind of always is going to be, unless I give you very easy examples. But you're not always going to see those real life examples be that cut and dry. So your task is going to be that your answer matches my answer. All right, nitrogen gas. This is the only thing that's listed, so it must be an element. Now, does it matter if it's N or N2? Nope, it doesn't matter because whatever it is, and it turns out it's this one, there's only one element, and that element is nitrogen. Now, nobody answered the pizza question in the chat, so you can quickly do that for me. But pizza is a heterogeneous mixture because every bite of pizza is different. For instance, when you bite from the normal end, which is like the center of the pizza, because you cut it into slices and you eat from the center out, those bites are going to be different from the crust end, which is going to be mostly bread and stuff. But what is the best pizza parlor? The correct answer that I always wait for my students to say is Zeke's Pizza. If you have not eaten at Zeke's Pizza, you should. Although I was told the other day, like, why are you advertising Zeke's Pizza to your students? They're students. Zeke's Pizza is expensive. And I was like, wow, I'm privileged. I never thought of that. Yeah, the pizzas are like, for a large, it's like $30. But it's one of the best pizzas that I've ever had. And like every single pizza that they make there, I've tried them all. And they're bizarre things like there's a Thai pizza that puts carrots and peanut butter on the pizza, and it's fantastic, and it has no right to be. Like all of them are so good. So go to Zeke's Pizza. It's really good, but it is expensive, and I realize that that's like a once in a while thing. This is the only element that's present, so this must be an element. There's another really good pizzeria in Belltown. I want to say it was called Belltown Pizza. Or is called that. I haven't been in years because I haven't been to downtown Seattle for quite a while. Thanks, pandemic. This is the one I actually want to talk about down here, steel. How do you make steel? Steel is one that a lot of people get mixed up on. And in order to answer this question correctly, the way that you need to do it is to consider how it's made. So how do you make steel? Well, you put iron into a container. You put all the other things that you're going to add, so like chromium, carbon, I listed manganese and nickel. I don't actually know these off the top of my head, but there are various different ways to make steel with all these different formulas. And when I say formula, I don't mean chemical formula. I mean like add this many grams of this and add this many grams of this, like a witch's brew kind of formula. And so you put it all in the container, you heat the hell out of it until it's molten. You mix it really well, and because it's a liquid, it'll become a homogeneous mixture, right? Then you pour it into whatever it is that you're going to cast for your steel. So usually that'd be like a girder or a beam or something like that. And once you've done that, it will then solidify and turn back into a solid, but it's still a mixture because there wasn't really a chemical formula to make it, just a recipe. That was the word I should have used, was recipe. So even though it's a solid, I misspelled homogeneous. Good job, me. Even though it's a solid, steel is a homogeneous mixture. Now, this is true for all substances that are called alloys. All alloys are heterogeneous mixtures. And an alloy is just a mixture of metals. So examples of alloys out there are things like brass, bronze, electrum, pewter, stainless steel, things like that. All right. So that's how we categorize these. And then there was some discussion about pizza. I was looking at the screen here. BLT pizza, I would totally eat. I want to say that my favorite pizza that I've ever had, it was the most bizarre thing ever. And the toppings were bacon, walnuts, and arugula on like a white sauce. And I ate it with blueberry beer. And I don't know what they put into it. I think the secret fifth ingredient must have been like crack cocaine or something. Because it was the best pizza I've ever had, bar none. And it was in Philadelphia, not in Philadelphia, sorry, Pittsburgh. Wow, I'm going to offend a bunch of people on the internet for mixing those two up. It was in Pittsburgh, right next to University of Pittsburgh. And I was visiting someone at the time, and we went out to that dinner. And then when I went back like a year later, that bar or pub had closed down, and I never got the recipe or like what actually was in it. And I will take it to my grave, the regret of not getting the information on this pizza. Oh, it's so sad. Sometimes you just don't realize you're in the good old days when you're eating the best pizza you'll ever have until it's too late. All right, let's finish the chapter. I'm going to paste a link in here. This is not a Rickroll. I actually cannot show you this link because I can do this. If you've ever heard this video, you will immediately recognize where this is from here. I mean, you would if I had any audio, so let me try that again here.
I miss you. How did this happen?
So, it's that video. If you've seen History of the World, I guess, by Bill Wirtz, let me link the video for you, actually. You can watch this on your own time. This is probably one of the best videos on YouTube, as indicated by the fact that there are 118 million views on this video. Like, that's more than 10 times the Rickroll video. But what this video shows is just, it is a... I don't think that Bill Wirtz is a scientist. He's a musician, for sure. Because he does all his music and all his own graphics, and it looks very interesting in its own style. If you open it up and you have seen this before, you've probably heard of it. It came out a few years ago, but this guy is analysis of like all the way from the Big Bang to today. So it starts off as physics, and then it goes to chemistry, and then it goes to biology, and then it basically becomes history. And like it's fascinating. And it's a 20-minute video. I'm not going to watch it, but the first 3 minutes of or so discuss how matter came about. So, like, there were just protons and neutrons and electrons everywhere, and then they came together, and then more of them came together, and now it's a star, and then the star exploded, and now you have everything. And so, all of the elements in the universe come from stars. Spoiler. However, most of that stuff is not reacted with yet. Now, this is the composition of the sun. The sun is very similar to the universe because it's just one random star of a collection of quintillions of them. There's tons of stars out there. I am using these numbers as an approximation, but recognize that the amount of hydrogen in the universe might be vastly different. I actually don't know the age of the sun and if we are a young star relative to everything else, which would mean we have more hydrogen available, or if we're an older star, which would mean we have less hydrogen than it would be on average. Because new stars are forming all the time and old stars are dying all the time. But anyway, the point is most of the universe is hydrogen and helium. I'm going to draw a line here. Inside that line is every other element that exists. So there's not much of the other stuff, but because there is so much stuff in the universe, you can find a lot of that and get it all together and get a planet, and then you get us, and then you get Chem 140. Now, because there are so many different elements out there, there's 118, you got to know some sort of method to identify each of them independently from one another. And so what we use are symbols. All symbols are a 1 or 2 letter code to represent the name of the substance, and most of them make sense. So like xenon is just the first 2 letters here. Oxygen, fluorine start with their letters. But you'll notice that for things like iron and sodium, they're based off of Latin names. And then for German, for tungsten, it's German. So most of the time you're going to see the first 1 or 2 letters. You do get some weird things. So for example, chlorine has an H in it, but nobody really remembers that because the symbol is Cl. For an ag major, what are the most important? Most important what? Can you be more specific? And by ag, I'm assuming you mean agriculture and not silver. So when you're writing the symbols, be careful. Also note the first letter is always capital, and the second is always lowercase. If you capitalize both letters, then everyone marks it wrong. Not just Canvas, but like me. As an ag major, you definitely want to know about carbon, but nitrogen. Nitrogen's a big one, and phosphorus, I think, because you need to have... Those are the things that plants use for fertilizer. Oxygen is a waste product, but it's also important to incorporate into cell matter. Honestly, I really could only speak from the biochem perspective. You can ask me about that in Discord. I can look up more information about like fertilizers, ammonium phosphate mostly, but there's other stuff in there. So like ammonium and phosphorus, those are important things to have. But as far as like nutrition is concerned, I'm not a botanist, so like I know magnesium is important because magnesium is the component of chlorophyll that I believe it's part of the electron transfer. Oh yeah, we're gonna run out of time here. Let me just finish the chapter real quick. There's not much left. Here's the periodic table. I pasted P table. Yeah, there it is up here. So in the links, it's right. Oops, you can't see my cursor. It's right here. So go to P table and look at it if you want to. This table I have right here is actually from Web Elements. You do not need to memorize the periodic table, but you should be aware of what I would call oddities on the periodic table. And an oddity is, I could get that one mixed up with another one if I'm not careful. So for instance, if I asked you to find tin on the periodic table, if you went here, that's an oddity. That's actually titanium. So tin is over here. Tin is a Latin name. And don't worry about it. I mean, I'll talk about anything for 2 hours. You guys are the ones who are paying to sit here and listen to me. So don't feel bad if you distract me. Another common one is phosphorus versus potassium. So if you're looking for phosphorus, that's P, but potassium is actually K. So again, look out for the Latin stuff. All the names will always be on every periodic table that you have access to for this class, unless for some reason you choose one that doesn't have names on it. I think it's silly that some instructors don't give you the names on periodic tables, because don't commit this to memory. Just look it up. And then finally, the way that we write formulas is you just index the number of each atom or of each element in the formula as a subscript right after. So H2O, there's 2 H's and 1 O. So I would write H2O like this. The brackets are just for me to indicate where we write. Here's ammonia. You don't ever put a 1 in your formula because that would be redundant and also increase the length of what is written. So anytime there's no number written, that is implied as 1. Again, don't do what I call lower caps. Don't do this. I should really get a different color here. Yeah, don't do this. If you have a lowercase capital letter, that's also wrong. Even if it is a smaller L or an R or whatever, don't do it. Just write. These are intended to be symbols and not letters. It'd be like saying, okay, well, this is the symbol for our element, and so you write it like this because that's your style. These are clearly different, so they would not be the same thing. In chemistry, these are intended not to be letters, but symbols, so they're supposed to be universal, so you got to write them the right way. Sometimes you'll see parentheses. Parentheses just mean, oh, okay, this number out here, you apply it to both things. However, it is written like that for a purpose because this is the polyatomic ion that we're looking at. If we write this implies something different and you lose a little bit of information. So sometimes you will be asked to write parentheses. For example, polyatomic ions. Other times I will have parentheses already in place for you. Don't remove parentheses and then distribute numbers through them. And then rewrite the formula because that would be incorrect. I'm not going to make you count how many atoms are in each formula, but you can do that if you'd like. But we are out of time, so that's the end of Unit 6, I believe. Yeah, hooray. Okay. That's good, because I need to get that quiz online for you. I'll do that after I eat dinner in a bit here. I'm going to put the quiz up for Units 4, 5, and 6, so you can take it. It'll be due next week, and then you'll be able to review the answer key before you take the exam. So that's why I wanted to get this done today. The Unit 7 and 8 quiz won't be assigned until... It'll be due after the exam, but there will still be stuff that you'll want to cover on it. So, Uh, we'll talk about the lab on when's the next class period we have this for this class? Tuesday. We'll talk about the lab tomorrow. The lab, I think lab number 2 is just density, so there's not really a ton to talk about there. But let's just do this here. So first I'll go here because it's easier for me to click there. So quiz number 3 will be due, let's see, Monday. And, oh, we're getting to May now, huh? Yeah, it's the 3rd. There you go. So we'll just put that at the bottom here. And yeah, that's more or less all I got. So have a wonderful evening. Thanks for coming to the lecture. Make sure you do quiz number 2. It's due tonight. And we'll see you tomorrow.